continuing from last time, where we talked about our amino acids and their properties and pKa values for some of their groups and R groups and amino and carboxylans. We'll put those together into protein chains and talk about some properties of these proteins. We'll save the assembly of the proteins, the translation, for the last lecture from this block, which will occur after this one. Okay, so let's begin with proteins. And we're going to label them in a hierarchy of structure. So we'll start out with a simple primary structure and build it all the way to a multi-subunit complex called the quaternary structure. So let's go through each one of those and see what it means. So starting at the most basic level, the primary structure of a protein is simply the sequence of amino acids in order from start to finish. Now, when I say from start to finish in order, there must be some directionality or orientation to the molecule, just like there was in our nucleic acids from 5' to 3'. We also have an orientation and a directionality in our proteins. And if you remember how we made the peptide bonds, there's a visual at the bottom there for you, where we took the carboxyl group of one and the amino group of the next and made that new amide or peptide bond between them. That's the order we're going to put them in. Is first amino acids carboxyl group is now interacting with the next amino acids amino group. So in order, it runs from amino to carboxy end. So the amino, the free amino side, is the beginning of the protein, and the free carboxyl end of the last amino acid assembled is the carboxyl or end of the protein. So that's our direction from amino to carboxy. And this is a question I always ask, and it gets most students, even with this warning that you're probably going to give me the wrong answer, and that's okay. It's how we learn from it. But let's review really quick on how things are made. If you're making DNA, you make it in what direction? And in fact, all nucleic acids are made in what direction?
Prime to 3'.
5' to 3', exactly, without exception. All nucleic acids are assembled 5' to 3'. The instructions for assembling that nucleic acid, be it a piece of DNA or a piece of RNA, whatever it might be, it's another nucleic acid, right? The template, as you will, is read in what direction? Without exception.
3 to 5.
3' to 5', exactly. It has to be in the opposite direction. When we're making protein, what direction is the template read, the mRNA template?
Three to 5.
It's actually read 5 to 3. And this is not an exception to the rule because we're not... This is not an exception to that rule because we're not making a nucleic acid. We're making a protein. So when we make proteins, we read the template mRNA 5' to 3'. And in what direction do we make the protein? So if we read the message, the mRNA, if we read the message 5' to 3', making protein, what direction do we make the protein?
Amino to carboxy group.
Exactly. So there are no 5s and 3s anymore. I get that answer quite a bit, which I'm happy I didn't. But if you were thinking 5 to 3 or 3 to 5, know that that's not involved in protein anymore. Proteins don't have 5' and 3' ends. They're not nucleic acids. So we assemble our protein amino to carboxy, or N to C. That's exactly right. And we'll talk about that more in our next lecture. But that gives you an idea of the direction of this primary structure. Okay, so if we go from one end to the other, and you list the amino acids, maybe the first one's a methionine, followed by a glycine, followed by an arginine, and then a proline, and then maybe another proline. And I go through the whole list all the way to the end, and I list them all out for you in order. That's the primary structure of a protein. It's a little more than an inventory of parts. I'm not just saying there's so many prolines and so many methionines and so many tryptophans. That's just an inventory. It doesn't tell you the order. So I need to give you the inventory of parts, but in what order are they assembled? That's primary. Okay? So what information can I get from primary structure, and what information can I not get? So let's do some examples. Can I get the mass of the protein from its primary structure?
Yes.
Yes, because I know all the parts, I know every molecule, every atom that's there, I can add them all up and get its overall mass. Can I tell you if this protein is going to be water soluble?
Yes,
Why would you say that?
depending on the amino acids that are making up the sequence, if it's polar or non-polar.
I do know that, exactly right. I know the amino acids and I know they're non-polar, polar, or so forth, but do I know which ones are going to be buried in the interior when it folds and which ones will be on the surface?
Not
You
necessarily. I mean, depends on the environment, perhaps.
Right, but from the primary structure, do I know that assembly? Do I know that shape?
Yeah.
No, not at all. So from the primary structure alone, I might have some idea of what amino acids I have and which ones are polar, which ones are non-polar, but I don't know how they're positioned relative to the solvent. Right? So I will not know if the thing is soluble in water or not. Now, if it's really short and you know it doesn't adopt a very complex structure, then you might have a guess. But for most proteins, the primary structure cannot tell you if it's going to be soluble or not. Right? It can't even tell you if it's going to be folded a certain way. There's no way to know from the primary structure alone. Okay?
Would you have to know like where the protein's headed?
You'd have to know its final destination, its environment, like you said. You'd have to know the pH of the solution it's in. All these other factors that are not in the primary structure's definition. So it doesn't tell you any of those things. But you can get the mass, and you can get, the length of the protein. If it were all stretched out, you can tell me how many lysines are in it. You can tell me lots of information, but nothing about its higher orders of structure, how it folds up, or secondary or tertiary. And we'll save those for those other levels of structure. Okay. So moving on to secondary structure, it's a little more complex. We zoom out a little bit, and secondary describes how the strand of amino acids, right? We have one amino acid connected to the next in this long chain here. How does it interact with itself on a short scale, right? So in very short distance relationships, like an alpha helix, which we'll talk about, or a little longer distance like a beta sheet, or it could be just a loop or a turn or something like that. So very small structures, not the entire protein. We'll get to that later. Okay, so secondary is how the protein interacts on a short scale with itself. Maybe how it turns on itself with a loop, or a simple turn, or an alpha helix, or a beta sheet, or something like that. Okay. If I continue zooming out, right, I make my magnification less and zoom out, see the whole protein, and I have all the parts of the protein in view, and I see how it's folded on itself, and there may be some alpha helices in this corner, and a beta pleated sheet over here, and some turns and loops, and all those secondary elements put together, and I see the entire protein. I'm going to call that the tertiary structure. And whereas with the primary structure, the definition was pretty simple. Just give me the order of amino acids N to C. Very rigorous mathematical definition, like it's methionine, glycine, proline, whatever it might be. Okay? For secondary structure, it's also fairly rigorous definitions of that's an alpha helix, that's a beta sheet, that's a loop, that's a turn, right? So you're kind of limited in your choices. For tertiary structure, you can get a little more flowery in your definition. Like that looks like a banana, right? Or this thing resembles my uncle's toupee, right? Or whatever it might be. You can give an idea of what it looks like with more descriptive language. You could also be very strict about it and say it's 25% alpha helix and it has an L shape, right? You can do that too. But you have more variety in how you describe tertiary structure. But what can I get from tertiary structure that I could not get before when I was only looking at primary?
How it folded?
How it's folded, exactly, which might give you a clue about what?
Solubility.
Exactly. Is it going to be soluble in water? Is it going to be bound to a membrane? Is it going to be buried in a lipid layer? Right? I can answer all those questions. What else can I answer that I could not answer before?
Possible function?
I might be able to deduce some function, right? It could be some groups on the surface that have a known arrangement, and if I see that, it might have a certain function, like an ATP binding domain, or this binds to a certain metal or something like that. That's true. What else? One more major thing. So I told you from primary you could get the mass, but does that indicate the size of the protein? But like physical size, volume?
No.
It depends how it's folded, right? Is it a long fiber, or is it curled up in a ball? Say that again? I couldn't quite understand what you said. So in a tertiary structure, I know how it's folded at this point. I know where everything is in three-dimensional space with respect to each. With respect. In tertiary structure. Can we please mute our microphone unless you're asking a question? In the tertiary structure, I can look at all the amino acids and all their atoms and see where they are with respect to each other in three-dimensional space. And at that point, I can tell you the size of the volume of the thing, right? And give you an idea how much space it will take up physically. Not necessarily its mass anymore, but how much space it takes up. Okay? And in some cases, not every case, but in many cases, if I zoom out even more, I can look at something called quaternary structure. So in quaternary structure, not all proteins have it, but in quaternary structure, there's more than one chain that comes together. So in this case, if I have one strand of amino acids from start to finish, N to C, and then I have another strand from N to C, and those two molecules fold up on themselves, forming each a tertiary structure, and then those associate with one another somehow. They bind together, they're just loosely associated, they form some kind of linkage between them, like a hydrogen bond, or a hydrophobic surface is buried, or whatever it might be. We have an association between two folded proteins. And we call that final structure, where they're together, the quaternary structure. Okay, so let's look at some of those as we go through in examples of. So can you please mute your microphone unless you're asking a question? Thank you. So let's look at some examples of those as we go through. So in our primary structure, we have a chain here from start to finish, and in this example, it's an insulin molecule. So we start at the beginning, we have chain A, and we start with glycine, isoleucine, valine, and so forth, all the way and end through tyrosine, cysteine, and asparagine. Okay, so that's the primary structure of the A chain in insulin. All right. Well, chain B, insulin also has a second chain. It's a totally separate protein. It's not connected to the first anymore by the peptide bonds. And it starts with phenylalanine, valine, and so forth, and ends with proline, lysine, alanine. Okay. So if we put those two together, or let them fold up on themselves and put them together, the whole structure of insulin. Another example down below, which is more a traditional example used to teach this, is on the bottom left, you have the primary structure of amino acids listed: lysine, lysine, glycine, glycine, all the way through histidine. And they fold up on themselves to make an alpha helix, which we'll talk about next, to make a secondary structure. Many alpha helices could come together, they're different sections of the same chain, and fold up to make that tertiary structure, perhaps found in myoglobin or one of the subunits of hemoglobin. And not in myoglobin, but in a molecule like hemoglobin, we have multiple subunits that come together to give it a quaternary structure, shown at the bottom right. And so in this case, 4 individual chains that have folded up, 2 that look like one type and 2 that look like another type, have come together to make this quaternary structure of 4 different chains. Not all of them will have 4 chains. Some have 6, 8, some have 3, some have 2. right? It varies, but I put multiple chains together to make a quaternary structure. In a molecule like myoglobin, however, only one chain exists, right? It's the only one, it's a monomer, there's no additional structures there, so it has no quaternary structure. Okay. So let's put them together in the primary structure real quick and see how the geometries have changed here. So looking at the very bottom first, we have our backbone there. These are all the amino acids put together with their amide or peptide bonds. And at the bottom, how do you know which direction this protein is going? From its amino to carboxy side, is that left to right or right to left on the screen? An easy way to figure that out is find the repeating unit. And the block on the top right, you see I've boxed in all the repeating units. So each amino acid will have an amino group, an alpha carbon, and then a carbonyl. Right? So an example, the second amino acid up there is glycine. There's an amino group, an alpha carbon with its R group, which is just an H, and a carbonyl. And then the bond to the next box is our peptide bond, and it begins the next amino acids, amino group, alpha carbon, carbonyl, and then on to the phenylalanine's amino group, alpha carbon, carbonyl. So if I'm reading it and I see amino, alpha carbon, carbonyl, NCC, NCC, I know I'm going in the right direction. So that one up top is going from left to right. Let's look at the one at the bottom. Pick a random nitrogen. I'm going to pick the one near the center. If I go left, I get nitrogen, carbonyl, alpha carbon. That's backwards. I need N, alpha carbon, carbonyl. So going the other way, I get nitrogen, alpha carbon, carbonyl. Alpha carbon is where the R group is attached, remember. Right? So NCC, carbonyl, NC carbonyl, NC carbonyl. The bottom strand is going left to right. And you can do that in any protein. Find an amino group, go one direction. If you run into a carbonyl right away, you're going the wrong way. It should be amino group, alpha carbon, carbonyl, amino, alpha, carbon, carbonyl. Then you're going in the right direction, or the direction we assembled it. Okay. What else do you notice about the structure at the top? And the bottom shows it as well. These are all L amino acids, right? So they all use their L conformation or levo conformation. So every other one, the R group is pointed either towards you or into the page, right? So at the bottom, you're showing the R group number 1 is pointed out towards you from the screen by the wedge, and then the dashes show R2 is pointed away from you in the next one, and R3 toward us, and R4 away, and R5 towards us, and R6 would be pointed away, and so forth. And that's also shown at the one at the top. So in this scenario, every time I look at a strand like this, if it were stretched out, which not many of them stay stretched out like this, but the beta sheets will, then the amino acids alternate which face of the strand they're on. So they'll face towards me and then away, towards me and then away. And if you rotate this 90 degrees along the axis, it'll be above and below, above and below, above and below. So you get that alternating pattern. Okay. All right, so you remember how to do these drawings. I want you to be able to do these on your own. And when you're done drawing it, you must go back and ask, are any of these going to be protonated or deprotonated? Well, we don't know how it's folded up yet, but let's say everything we've drawn is on the surface and accessible to solvent. And we need to change some of the R groups, as well as the terminal amino and terminal carboxyl groups. And you have your chart here of their pKa's. So given a pH, say 7 in this example, and you draw out glycine, phenylalanine, aspartate, and then serine, which of those amino acids might you consider changing their protonation state? Well, glycine doesn't have a pKa, not one in our range we're interested in. And so we'll leave glycine alone. We'll just get a hydrogen. Phenylalanine, same thing, just a hydrophobic thing. But aspartate, right, or aspartic acid will be in one of those two forms, either protonated or deprotonated. And we need to know its pKa. Well, it's aspartic acid, so it's a carboxylic acid. It's somewhere around 2 to 4 in that range. So at pH 7, we need to think 7, the environment, pH 7, is far more basic than that amino acid's pKa of around 2 to 4. So it will most definitely be deprotonated, right? We're far more basic than the amino acid's pKa. So the ratio of its deprotonated state to protonated state will be high, right, to compensate for the increase in pH. Serine's not in our list. It has a pKa of about 16, so don't worry about it being ever deprotonated. at least not in the normal case. Okay, so that's how you would go through those, draw all their structures, draw the backbone first, don't forget the hydrogens on nitrogen, right? And then go put in your amino acids R groups and then decide, in this case only one matters, the aspartic acid, what protonation state it should be in based on the pKa and the environment's pH. So always compare the pH to the pKa. And then again, when we draw these out, make sure you get the planarity correct, or the chirality correct. But I'm not going to ask you to draw those out on the test, but know that the things are chiral, right? That the carbon, the alpha carbon, is a chiral center, unless it's glycine, of course. But let me go back real quick. If you look at the bottom of the screen here, any particular peptide bond, we can pick one, right? So I picked one right here in the center of the screen. We have the carbonyl of amino acid number 2 and the amino group of amino acid number 3, and they're forming a peptide bond. You can look at any peptide bond you'd like in the drawing, but because they're all equivalent. But you notice there's a carbonyl there, right? So the geometry around that carbonyl, think back to organic, would have what molecular geometry? There are no lone pairs on the carbon, so its electronic and molecular geometries are the same, and it would have what shape around the carbon?
Trigonal planar?
Yes, it'd be trigonal planar. So what are the physical consequences of being trigonal planar? It says it in the name. What does that mean? What does it look like?
It's flat.
It's flat. So the three things attached to this carbon are all in the same plane. So in other words, the oxygen of the carbonyl, the alpha carbon that precedes it, and the amino group nitrogen that comes after it are all in the same plane. Okay? This carbon has no hydrogen on it. It has no lone pairs. It's perfectly planar. Okay? Which bonds are what's the geometry around the previous carbon? The carbonyl carbon, right before it is an alpha carbon. So what's the geometry around that alpha carbon?
Tetrahedral.
It's tetrahedral. Again, no lone pairs, but it has 4 things attached, right? 4 Vesper groups. You remember that computational method. So 4 Vesper groups around it. It adopts a tetrahedral formation, and these 4 bonds are free to rotate, right? Not that it means much on the bond to the hydrogen, but the other 3 bonds are free to rotate. Right? So these are the phi and psi angles, the ones in the backbone, and the rotation, the bond to the R group is free to rotate as well, with one exception, and that's when it's proline, because it wraps back and rounds to the nitrogen, making a ring that can't bend. Right? You can't rotate a ring structure. So let's look at the next bond. From the carbonyl carbon onto the next amino acid's nitrogen, this is our peptide bond. Does that look like it's free to rotate? It's a single bond. What do you think?
Did you say the nitrogen?
The bond between the carbonyl and the next amino acid's nitrogen, or the peptide bond, it's a single bond. Is it free to rotate?
No, because the carbon is sp2 hybridized.
Well, the carbon being hybridized doesn't affect the bond's ability to rotate yet, not per se. It looks like
The single should rotate.
single bonds should rotate, right? They do. But he had it almost at the answer there. But this peptide bond is not free to rotate. Let's think about why. Okay, so looking back at this drawing at the top of the screen, this CO linkage at the top is not shown as a double bond, but we know it is a double bond, which makes all these other atoms you see in here, the alpha carbon, the oxygen, and the nitrogen, all in the same plane, indicated by this little shaded region, right? So they're all in the same plane with this carbon. However, when you have a carbonyl next to a nitrogen like this, it could be another carbon as well, you have something called Keto-Enol Tautomerism. You guys remember that from organic? Where you have a carbonyl and another, in this case, nitrogen, but it could be a carbon as well. You can form a double bond between the carbon nitrogen instead, and this becomes an OH attached, right? Or in the case where this is a carbon instead of a nitrogen, in our typical Keto-Enol Tautomerism, you put a double bond between the 2 carbons, and you still have an OH. So it'd be an alkene and an alcohol, so it's called an enol, or you have it in its keto formation where it's a carbonyl. Okay? This peptide bond can also adopt those 2 resonance forms. right? And of course, the carbonyl one is more stable because the oxygen is more electronegative, but there is some percentage of time it spends with the double bonds between the carbon and nitrogen. The fact that that's not an insignificant amount of time spent in that formation means the carbon-nitrogen bond behaves as though it's a double bond. So the peptide bond has double bond characteristics, which means it cannot do what?
Rotate.
It cannot rotate. So we're going to treat it as if it were a double bond as well, as far as the geometry is concerned, which also means this nitrogen is experiencing what geometry? It has a double bond and two single bonds.
Trigonoplanar.
Right? It's going to look trigonal planar again, right? It won't have a lone pair anymore because it's forming four bonds, but it will have a positive charge at that point in that resonance structure. However, the bonds will give it a trigonal planar geometry, meaning this nitrogen, along with the three things it's bonded to, the hydrogen, the carbonyl carbon, which was a carbonyl carbon, it's now just a carbon, and the next alpha carbon are all in the same plane. Well, consecutive centers that have trigonal planar geometry means that all six of these atoms are in the same plane, right? So this planar bond, this peptide bond, is essentially totally planar and all six atoms are in the same plane. So our peptide bonds are not free to rotate. What bonds are left free to rotate? Of course, the bond to the hydrogen can rotate, which is meaningless because it's just a single atom. And the bond to the oxygen, whether it could or could not rotate, which it can't, is still irrelevant. It's a single atom. But the bonds between the previous alpha carbon and this carbon, and the nitrogen and the next alpha carbon are both free to rotate. Those are our phi and psi angles of the backbone. And that's the only part of the peptide chain that's free to change its geometry. So when I say our protein folds up, it's not able to adopt any old conformation. It's sort of restricted. All right, here's a picture of that.
So you're saying that the first carbon, alpha carbon, can rotate freely in relation to the nitrogen, right?
The alpha carbon at the top left here, its bond to what was the carbonyl carbon is free to rotate. So if you imagine this bond rotating, and these three groups here can rotate around this bond.
Okay.
Same thing on this end. The nitrogen to the alpha carbon, these groups are free to rotate amongst themselves, this bond rotating. But the carbon-nitrogen bond in the center of the peptide, right, between two amino acids, the peptide bond between them is considered planar, making all of this region unable to rotate. I cannot rotate this bond in the center. Okay.
Thank you.
So here's an example of that from organic when you're thinking about Keto-Enol Tautomerism. So the one on the left would be your keto form, and one on the right would be your enol form, right? And it resonates between the two. Of course, in this case, the keto form is far more stable than this double bonded carbon with an O minus. But we have a nitrogen here, so that it's a little more closely related to each other. We still prefer the keto form, but because the other one is less insignificant and more significant, we're going to treat this bond as planar. Okay? And then I have a difference here. So why is it almost all peptide bonds are in the trans arrangement? Remember, this is treated as though it were a double bond, so it could have cis-trans possibilities. Why are almost all peptide bonds, about 1,000 to 1 likelihood, they're in the trans arrangement? And don't say because it's more stable. That's not the answer I'm looking for. Tell me why it's more stable. So why is a trans arrangement preferred?
Does it have to do with nitrogen being an electron donor?
No, just why is a trans arrangement in general for a double bond preferred over a cis?
Steric hindrance?
Or less steric hindrance, right?
Yes.
So in the top figure, I could make this cis by switching the hydrogen at the top with the entire group on the right, the alpha carbon and beyond. If I switch those two, this would be a cis arrangement. But then our two alpha carbons would be much closer together, and you may have some clashes between their R groups, right? So if you keep it trans, you're more likely to have, or less likely to have those clashes. That's the reason why we consider it more stable. Okay, with almost an exception. It's not quite an exception, but when you have a proline there, right? So when you have a proline, the arrangement is a little constrained, right? It's not necessarily purely stable trans anymore because you have that ring structure of the alpha carbon here wrapping around back to its nitrogen. So in a protein, when you have a proline residue showing up, the preceding peptide bond that leads to the proline isn't more likely to be cis at all. It's still more likely to be trans, but it's only a 3 to 1 times more likely, right? So instead of 1,000 to 1, it's only something like 300 to 1, right? It's still far more likely to be trans, but its tendency to be cis is a little more than if it were not a proline. That's what this 3 to 1 means. So it still would much rather be trans, but the trans to cis ratio that it occurs is only about 300 to 1 rather than 1,000 to 1. So don't think it's more likely to be cis. It's more likely to be cis than if it were a different amino acid, but it still prefers trans. Maybe those wording will make sense when you see the numbers. I don't know why there's 2 number 2s on here. It should say number 3. Okay, so let's look at our bonds that can rotate. And I said again, you have your peptide bond here, which cannot rotate. So that's between the carbonyl and the next nitrogen. So peptide bond here can't rotate. Then you have this amino acid shown in the center with its amino group, alpha carbon, R group on it, carbonyl. And then the peptide bond to the next one, again, cannot rotate. So we have 2 angles in there where the alpha carbon to carbonyl bond, right, was our psi bond. And then our amino group to alpha carbon is our phi bond, right? So you have phi and psi angles. Those can rotate. This molecule...
I have a question.
Yeah, go ahead.
Can you go back over number 3 on the last slide?
Yes, so when you have a peptide bond, the chance of it being trans versus cis is about 1,000 to 1 for almost all the amino acids. But when you have a proline in the sequence, that bond that precedes the proline, the alpha carbon, carbonyl, and then next amino acid being proline, that carbonyl to nitrogen bond, is only about 300 times as likely to be trans versus cis. So it's prefers trans by far, but that 300 or 330 to 1 or something like that is 3 times more likely to be cis than if it were not proline. Does that make sense? I'm not saying it prefers cis at all. I'm saying the chance of it being cis is greater when it's a proline. It's still only a 300 to 1 ratio, but it's not 1,000 to 1 anymore. Does that make sense?
Yes, thank you.
Okay, so don't say it's more likely to be cis than trans. It's more likely to be cis than other amino acids' chance of being cis. That's what that 3 to 1 means. Okay, so let's take the structure in panel A here and turn it on end as if you're looking down the chain, right? You're looking down these bonds, and that's what's shown in panel B. So this phi and psi angles here. So the phi is the angle between these bonds, so it's a diangle. So what it means is I look down this carbon-nitrogen bond here, right? And I look down this carbon-carbon bond here, and the angle between the 2 of them would be this phi angle. Same thing with psi. I look down the carbon-nitrogen bond and the other nitrogen-carbon bond, and the angle between them would be the psi angle. Okay? And these are free to rotate, we said, but they can't just be any haphazard angle. Not everything's allowed. So when they started deciphering protein structures, you get crystal structures, and we saw them in 3D, and they started looking at all these possible angles for what happens in reality. Someone decided to make a plot. So what could the phi or psi angles be? Well, we said they're free to rotate completely. So they could be anywhere from negative 180 degrees all the way to a positive 180 degrees, choosing 0 as our point of reference, which is basically all the way around. We just don't call it 0 to 360. It could turn 180 degrees one direction or up to 180 the other direction, and that's 360 degrees. We do the same thing when we talk about our longitudes on a globe. we don't call it 0 to 360. We do 180 degrees west and 180 degrees east, and they meet at the international date line, which is 180 degrees in either direction. We don't call it 360. So same type of thing here. We can be anywhere from negative 180 to positive 180 for either one. And we plot those on a chart, which was described first by a researcher called Ramachandran, so it's named after him. And if you look at all those angles, when you plot them, they tend to cluster in regions, right? Not every possible angle is represented. So some regions are favored, shown in the dark green here, and some regions are not so favored, but not disallowed completely. And some regions, which are never represented, are here this disfavored region, where you get these steric clashes. The bonds are still trans, right, for the most part, but some of them are in here are the cis accommodations, and they're not allowed very much, or disfavored. So virtually 3/4 of the space is not shaded any shade of green at all. So almost 3/4 of all possible combinations are not seen. They're hindered in some way by a clash, or they're just disfavored. Right? So only about 1/4 is seen, and even the more selective part of that is the really favored ones, or the ones we see most common. And that's because those occur in specific structures of secondary structure, such as an alpha helix or a beta sheet. Right? And that's what we'll talk about next. If we get those orientations, we have an alpha helix or a beta sheet. Right? What is an alpha helix? So we're starting to describe secondary levels of structure now. So on the bottom of the screen here, you have some random piece of protein, and it folds up on itself. Right? So this is the typical coil you see in the ribbon drawings, and it's called an alpha helix. Right? So our alpha helix is twisting on itself, and it's almost always, and for your purposes, we're going to say always, twists in a right-hand twist, and that's a consequence of them being all L amino acids. So it twists in a right-hand coil. Whether you look at it from bottom to top or top to bottom, take your right hand and follow the curvature of that coil, and your hand will twist around it easily. If you try to do it with your left hand, it's not so easy to do. Your hand is in an awkward position. So this is a right-handed twist. How is it held together? All secondary structure is held together exclusively by hydrogen bonding. Right? And the hydrogen bonding is occurring among the backbone. The R groups aren't much involved here. So the hydrogen bonding occurs between the amino group on the backbone and the carbonyl on the backbone, but not necessarily the ones right next to each other. That's too close. So a hydrogen bond is roughly 2.5 to 3.5 angstroms between the two. Right? So between the the oxygen of the carbonyl and the nitrogen of the amino group, the nitrogen having the proton on it, or the hydrogen, the distance between those is about, on average, 3 or so angstroms. So 2.5 to 3.5 angstroms. Where the bond between the nitrogen and hydrogen is about 1 angstrom, and the bond between the hydrogen is not a bona fide true bond, it's the hydrogen bond, it's the association between the hydrogen and the oxygen of the carbonyl is roughly about 2 angstroms. So total about 3. Okay, so if we keep doing that, and every carbonyl bonds to every amino group it can down the chain, will form this alpha helical structure. Okay, and the structure on the left is sort of confusing at first, so let's look at the one on the right, where it's simplified. And what we're showing is just the atoms that make up the backbone, like I was counting earlier. The nitrogen, alpha carbon, carbonyl, nitrogen, alpha carbon, carbonyl. But we're not showing the oxygens here, just showing the NCC. And you see this chain is going up or down. Well, let's figure it out. Pick a nitrogen. Let's pick this one in the center, right? Or this one, actually in the center. So if I pick this and I move one direction and I go this way and I end up at a carbonyl carbon, how do I know it's a carbonyl? The oxygen is not shown. They labeled it as the lighter gray for you. So this is a carbonyl. I'm going the wrong way. So I should use nitrogen, alpha carbon, which is the black one here, and then carbonyl. Nitrogen, alpha carbon, carbonyl. Nitrogen, alpha carbon, carbonyl. So this protein is going from bottom to top, right, as it rotates. And you see it's rotating around. If you use your right hand, as he's showing in the picture here, show your right hand going around this thing. Your hand will twist upwards as you turn it. Okay? So what's actually holding it together, right? And we said hydrogen bonding. So this amino group, let's pick the same one I had again. Let's remove the pole in the center for clarity. Here's our amino group one more time. It has a hydrogen on it. And its hydrogen bond with this one down here, this carbonyl carbon has an oxygen on it. You can't see it in this picture, but it's behind the bond here. and they're hydrogen bonding, shown by the yellow dash here. Okay? And if you work your way up the structure, every amino group is hydrogen bonding to the carbonyl that's exactly 4 amino acids down the chain. So there's a mathematical relationship here. The amino group is hydrogen bonding to the carbonyl that is 4 amino acids down the chain. Okay, so let's do a little math. We did this for our DNA and RNA structure, so we'll do it for a protein as well. We asked, how much does it take, or how long does it take for the thing to turn all the way around? Well, for nucleic acid chain, like RNA or DNA, how far do you have to go along the axis for it to turn all the way around? Well, we did our answer in angstroms, and what was it? A typical B-form DNA to turn all the way around was how far? Guys remember?
34.
34 what? The unit's important.
Angstrom.
34 angstroms, good. And an angstrom is 1/10 of a nanometer. So 34 angstroms would be 3.4 nanometers, right? So we can put it in a number that compares with what we have here. So in this case, to turn all the way around from this point to where that point occurs again is 54, right? Or 0.54 nanometers, which would be how many angstroms? So 0.54 nanometers would be how many angstroms?
54.
Not 54, but
5.4.
5.4, right? So 5.4 angstroms is much, much shorter than the long DNA we had to do it, right? We're talking dozens of angstroms for the DNA to turn around. Where here we're doing it in 5.4. So our alpha helix in our protein is making a much tighter turn than the really broad turning radius. So it's like a semi-truck turning around for our nucleic acids. And that makes sense because our nucleic acids have all this interior stuff that has to turn around. It's a big vehicle. Whereas in our protein here, the alpha helix is wrapping as tightly as it can around this pole, right? There's no interior space at all. And all the R groups are going to point outward, not interior. They're going to point exterior. So we can turn around very rapidly. So it's like a golf cart turning around instead of a semi-truck, right? Everything points outward instead of inward. Right? So the other thing is, when we asked in DNA, it took so many angstroms to turn around. How many bases did it take to do that turn? So to turn completely around, how many bases did it take? How many base pairs?
10.
Right, so it took about 10 to turn all the way around. Here, if I say each rise in amino acid is 0.15, right, and the total to turn all the way around is 0.54, how would you find out how many it takes? I'm not looking for you to do the math here. This isn't a math question. This is a can you set up the problem question. If it takes so far to turn all the way around, and each amino acid rises this far, how can you calculate how many amino acids it takes to turn all the way around?
Pitch over rise?
Exactly. I take the total distance divided by how far each one moves it, and I get how many it takes. Well, here, not so fortunately, it doesn't come out to a whole number, right? Where DNA was very, very close to 10, so we use 10. Here, it's not even close to a whole number. So if you take 0.54 and divide it by 0.15, you get 3.6. Okay? So it takes 3 amino acids to turn all the way around. That's why when you look at it on this picture, when I'm equating equivalent spaces, they don't look the same. It's turned some, right? It's not exactly in the same radial position as it was, but it is the same position on the side. Okay? So if it takes 3.6 amino acids, this part's convenient, to turn all the way around, what's the angle between each one? Let's think back to DNA real quick. We said it took 10 to turn all the way around. All the way around is 360 degrees. So each one turned 36 degrees. I know you could do that math easily. This one's just as easy. 360 degrees all the way around, and it takes 3.6 to turn around. How far does each one turn?
100 degrees.
100 degrees, exactly. So it's a little more than a quarter turn, right? Quarter turn being 90 degrees. So the amino acids do not stack on top of each other exactly, right? They're turned 100 degrees to each other. So they're not exactly on top of each other. So by the time you go all the way around, there's a 40-degree bias, right? We turned 100, 200, 300, 400 degrees. So in that last turn, we're 40 degrees past where we started, right? So this is why the amino acids are hydrogen bonding with 4 down the chain, because it's around a full turn. But you notice those hydrogen bonds on the left are not vertical. They're at an angle, right? They're slightly tilted because it's at 400 degrees all the way around, or 40 degrees from where we were, not 360 to get to the next amino acid. Okay? All right, and all those numbers are here at the bottom. You answer those questions exactly. 100 degrees per residue turn, 3.6 per total turnaround. So like RNA and DNA, I want you to learn those numbers, and you can compare how they would twist compared to a DNA helix. Right, so this is shown again. We have our carbonyl bonding to our amino group, and it's 4 residues away, so amino acid N will hydrogen bond to amino acid N plus 4 down the chain. And how many hydrogen bonds do you think an alpha helix at a minimum would need to hold it together? Absolute minimum, how many hydrogen bonds would it take? It's kind of a trick question. You need at least 1. If you have none, you have nothing holding it together. So we need at least 1 hydrogen bond to hold anything together. So what's the minimum number of amino acids that an alpha helix can contain and still be an alpha helix?
4.
Not 4, but if I only had 4 residues, the first one would pair with what number residue?
4.
If N is 1, it would pair with N plus 4.
5.
I'd need a 5th one to have a hydrogen bond. So the minimum length of an alpha helix is what?
5.
I need 5 amino acid residues, yes, at minimum to make an alpha helix, right? How many could I put in it? What's the longest it can be?
It should go on indefinitely, right?
Yeah, there's no reason that we have no constraint to say mathematically it could go on forever. We know it doesn't. So there must be some reason not to keep it going forever. And there are some that are exceedingly long, hundreds and multiples of hundreds long. And those are our cable-like proteins when we get to keratin and collagen and things like that. But for the most part, outside of those cables, the longest alpha helix that we see is one that serves a purpose, right? And what might an alpha helix do? It might need to cross a membrane, right? So crossing a membrane might put constraints on how long we actually see alpha helices adopt. And that's generally as long as they get, somewhere around 40 or so amino acids long. One other feature of it that you won't see from a short amino acid, you have to look at long amino acids, is that they don't run straight. So if you look at an alpha helix shown in a drawing, like the one on the bottom there, it looks like it's running in a straight line. But if you make it long enough, they have an ever so slight curvature to them, right? So they don't run straight. There's an ever so slight curvature to the helix. It curves on itself just slightly. And we'll see how that's useful in just a minute. Okay? So what amino acids can be put in alpha helices? Right? We could think you could put any one you want, right? Seems like it makes sense. They all just point out towards radially from the periphery. But not everyone will do. If you put very, very large amino acids out there, R groups, they tend to distort the helix. So we don't want to put really big things out there. We also don't want to put something too small, like a glycine, which is kind of like not putting any R group at all. It doesn't take up any real space, right? So very common is just put a small amino acid out there, like alanine, right? Or a small polar one like serine, right? So very small amino acids are common in alpha helix. That's not to say the others don't exist, they do, but they're less likely, right? Proline is the least common thing you want to put in a helix because it prevents the curvature that we need. We need those phi and psi angles to be in that negative 45 angle range, right? In that box we were talking about earlier. So if you put a proline in there, it precludes having that angle. So a proline is a great way to break a helix, right? It seems like that would be a bad thing to do, but if I want to stop a helix, proline would be a good choice, right? So maybe I have a helix going in one direction and I need to stop and turn it. Proline would be a great way to do that. Right, so here's some stats on alpha helices. If you look at every protein structure ever published, and you started calculating what percentage of the amino acids are in alpha helices in these proteins, it comes up to about 1/4. Right? So if you look at across the board, what percentage of amino acids in every protein structure we've ever seen, I don't mean on a bulk matter, I mean just from a statistical point of view of it exists. What percent of amino acids are in an alpha helix? It's about 1 out of every 4, right? So about 26% or so. And they vary between 5 and about 40 residues, and we already talked about why those limits generally exist. But if you take it, turn it on its end, like shown in panel C here, it looks like there's a hole down the middle, but there is not. This is not a space-filling model, it's just a ball and stick model. If you look at the size of the atoms themselves compared to those bond lengths, panel D shows you it's completely filled space. There's no empty space. It's not a channel. Alpha helices could be used to make a channel. We'll talk about those too. But one individual helix is not a channel. Okay. Okay, let's move on to beta sheets real quick. We'll get through this one easier because you already have an idea of what the hydrogen bonds are. And in this case, we're taking the strands and not coiling them on themselves at a very close range, like n to n+4, but we're stretching them out and laying them down side by side, like 2 spaghetti strands next to each other. But again, the chains have direction, and if you look at the sheet on the left, it's labeled A. How do I know that that strand is going, as the yellow arrow indicates, from right to left on the screen? How do I know it's going that way, other than the yellow arrow telling me? Is the yellow arrow even correct?
The order of the backbone.
Ordering of the backbone again. Think back to that primary structure thing. It's N alpha carbon carbonyl, N alpha carbon carbonyl. And if you see that and follow it, it goes right to left. The strand it's bonding to below it is going left to right by the same rationale, right? N alpha carbon carbonyl is going left to right. So these 2 strands are going in opposite directions, much like our DNA strands and RNA strands do when they bind. And so we call them anti-parallel. Just like the strands in DNA and RNA are called anti-parallel. They're going in opposite directions when they pair. Okay? The one below that in panel B, they're both going in the same direction. Now, RNA and DNA can't do this, but proteins can. So going in the same direction at the one below, we call these parallel beta sheets. And they're not quite as stable as the anti-parallel ones. From the drawing, can you tell me why an anti-parallel sheet is ever so slightly more stable than the parallel beta strand arrangement?
More bonds, hydrogen bonds.
So not necessarily more per unit length. There's about the same number. You see there's 6 hydrogen bonds at the top one, and it's only showing the 4 there, but there's going to occur 2 more right after that. So it's not so much a number of hydrogen bonds. There's something else more important. Right, so go ahead.
Is it just the angle?
It's the angle, right? So if you want to attach these 2 things, and if you put their gluing, the hydrogen bonding, perpendicular to their orientations, that's the strongest way to glue them together. If you put it at an angle, only the proportion that's perpendicular is actually holding them together, right? You remember this from physics when you put angles and forces. So if you put them perpendicular to each other, it's going to hold more tightly. So that's why parallels aren't as strong as anti-parallels, because the angle is not 90 degrees to the direction. But you can also have mixed beta sheets like the one on the right, where you have 2 strands going in the same direction on top, and then the bottom one's going in the other direction. And they're all hydrogen bonding to each other. And you can get some kind of mixture like this as well. Right? So, quick question, and I'll answer it. It's a hypothetical question. In the arrangement for an alpha helix, you had amino acid N hydrogen bonding to amino acid N plus 4, we had a mathematical relationship. What kind of relationship exists for our beta sheets like this? Do we have some kind of relationship for that? And in fact, no, we don't, right? I don't want to leave you hanging for that for too long because there is no answer to it. That top strand can run off and do a dozen other things before it comes back and binds to the strand again. There's no reason it could be 50 or 60 or 200 amino acids later. And there's no constraint on how far it can go before it comes back. So there is no mathematical relationship on who's hydrogen bonding with whom in a beta sheet. However, it does exist in an alpha helix. It's a closer association. All right, so just like the alpha helix, if I said an isolated alpha helix, and if you looked at it, it looked straight, twisting on itself, but it does have a slight curvature to it. And I'll show a picture of that in a second. But in the beta sheet here, if you put a bunch of beta strands together, like at the bottom of the page here on the right, if we put many more of them, they don't lay flat with respect to each other. They have this propeller twist. A is trying to show it with shading, but it's easier seen in panel B, where you notice one strand is not exactly aligned with the next. It's a slight propeller twist to it. Right? If I take these strands and take the very ends of them, the last strands on the end, and sort of wrap this into a cylinder, right? So if I take, maybe there's 11, 12, 17 strands, whatever it might be, and I wrap them into a cylinder, I get what's called a beta barrel shown on the bottom, right? So if you look at the bottom, when it's just a bunch of beta strands forming a beta sheet, but they eventually wrap around to where they started. Because of this propeller twist, you can make a cylinder, right? A barrel here. This could be used as a pour. It could be used as a molecular tin can to store something in. You see that as well. That's how green fluorescent protein works, right? Or you can make this into porins to punch holes in membranes and such. Okay. The panel C at the bottom on the left is showing a beta pleat in green with a slight twist to it that's connected by a pair of alpha helices. And this is showing you that the two alpha helices you see, each alpha helix isn't necessarily straight. They have a slight curvature to them. Okay? And the one at the bottom actually has a kink in the chain. You notice there's a pair of cysteines there forming a disulfide bond, kinking the alpha helical chain. Okay? The last part of secondary structure is called loops and turns. So we said about a quarter on average of a protein is alpha helix. A protein could exist with no alpha helix at all. That's entirely possible. I'm just saying on average it occurs about a quarter of the time. However, in a typical protein, and this is true for most proteins, about a third of the amino acids aren't involved in alpha helices or beta sheets at all. They're involved in something called loops, right? Or loops and turns. Okay, so here's a little hierarchy here. All loops are present. That's my 1/3, right? Some of those loops are called turns. Not all turns, not all loops are turns, but all turns are in the loop category. It's a subset of loops. Okay? And what I mean by that is if it's not organized into a sheet or organized into a helix, we're going to call it a loop. Right? It's just this wild piece sitting out there. We call it a loop. That's all it's really doing is going from point A to point B. Right? It's not really taking on any structure per se. Not an alpha helix, not a beta sheet. Some of those loops are rather short. Right? All they do is reconnect two ends of a beta strand or so. And there's an example of that right here, where it just quickly turns around, like this example right here in B, where it just quickly turns around and we're going down the next strand. Right? So loops are the unorganized, not strands, not alpha helix part of a protein. They're still called secondary structures, but turns are a subset of loops that are simply just a quick turnaround, like a U-turn. Right? It's what it makes into a protein. It connects two other elements. More specifically, if that turn connects two strands of an anti-parallel beta sheet, it's called a beta turn, right? Or a reverse turn. Right? It's a U-turn. It turns around. This could not happen for parallel beta strands because if you're going to connect two strands that are parallel, it's got to go all the way to the other end because they're going in the same direction. So it can't be a short turn at all. So it's not a turn. It'd just be a loop. So everybody get the hierarchy of these loops and turns. There's lots of loops. They're the unorganized stuff. Some loops are called turns because they're really short. They turn around. Some of those turns are specifically called beta turns because they connect the strands of anti-parallel beta sheets. There's no such thing as an alpha turn or anything like that. I see those sometimes on tests. I'll make up the answer. It's loops, turns, beta turns. One's a subset of the one before it. Okay, and that concludes our secondary structure stuff. So you had alpha helix, beta sheet, and then loops, some of which were turns, some of which of those are beta turns. Okay. All right, let's zoom out a little more and look at tertiary structure. Here we're going to see the entire protein, such as that molecule on the bottom right. So this is a ribonuclease, for example. This cuts RNA. Right? This might be our RNase that we use to cut up a piece of RNA. So it has some structures you see in it. I see an alpha helix. In fact, I see a few of them. I see a beta sheet that's kind of twisted on itself, and it looks like they're going in opposite directions everywhere they pair. So that's an anti-parallel beta sheet. There's quite a few strands to it. I also see some disulfide bonds. Looks like little lightning bolts. Right? So they're colored yellow like we typically do for sulfur. And so they're connecting different strands with a covalent bond, a disulfide bond. And we also have some loops in there, like the purple stuff. It's just kind of unwieldy, not really organized, but it's connecting other secondary elements. Okay? So this whole thing as a group, we look at the protein, we zoom out, and we say it kind of looks like insert down here, right? Whatever you want to call that thing. It might be sort of L-shaped, or it might look like a violin to someone, or whatever it looks like to you, right? That's its tertiary structure. So let's recap really quick. What held primary structure together? What was the only thing that held primary structure together?
Peptide bonds.
The peptide bonds. And chemically, those are amide bonds, right? Or amide bonds. What's the only type of bond that holds secondary structures together?
Hydrogen bonds.
Hydrogen bonding. And hydrogen bonding specifically between the backbones, right? The backbone carbonyls, the backbone amines. What holds tertiary structure together? Well, that's a long answer, right? Everything, all these things. We have disulfide bonds, that's covalent. We have some hydrogen bonds. It could be between backbones. It could involve R groups. We have salt bridges, like ionic bonds between positive and negative charge things. We could have some hydrophobic interactions, right? So there's lots of possibilities here that can hold tertiary structure together. If you can think of a connection, it can hold tertiary structure together. So vast diversity of things that can hold tertiary together. So it's a big difference from the first two. Okay. So let's practice real quick. Here's a really quick practice test for you. Select the type of tertiary interaction that we see between these type of things or amino acids at the bottom. So let's do it this way. Let's look at choice A. A is, what interaction could we see between a leucine and a valine? And this is more of a test of do you know your amino acids than anything else. So a leucine and a valine, both of those are just hydrocarbons, right? Greasy, hydrophobic amino acids. So that's only going to be a hydrophobic interaction, right? They can't do anything else. So what kind of interaction would we see between B, two cysteines? Well, we know cysteine is the only amino acid that can form the disulfide bonds, so we're going to pick disulfide there. Between an aspartic acid and a lysine, or more appropriately said, aspartate and a lysine, would be what?
Ionic.
That'll be our ionic or our salt bridge type of interaction, where you have one positively charged and one negatively charged. The last one says serine and threonine, or those are both in the category of alcohols, right? They're hydroxy groups, and those are going to likely form the hydrogen bonding between the two of them, right? Because that's easily what the oxygen can do there. Okay, so be able to tell what amino acids could do what in a protein. Right? All of these could be parts of tertiary interactions. Right? So here's some examples of tertiary molecules or tertiary protein arrangements. We have very simple ones like collagen and keratin, or they're long, thin fibers. Right? So we call those fibrous proteins. We could have it fold up into a little ball or a sphere. We're going to call those globular because they look globe-shaped. And we're going to call many things that are even remotely close to globe-shaped globular. It might be bulky or have bulges on it. We'll still call it globular because it's not a long, thin fiber. right? So we're going to save fibrous for the long, thin ones. And then the last type was more of a occupational, or where you reside, than what shape you have, and it's found in a membrane. And membrane proteins are kind of inside-out proteins compared to globular, because they have to be in a hydrophobic environment, not a hydrophilic environment. So the amino acids on the surface are going to be reverse those that are in a solution of water. So let's look at the first one. Here's some example of keratin. And keratin is one of those really long, hundreds of amino acid alpha helical things, where, remember, if I said you get it really long enough, it doesn't stay straight. It has a slight twist to it, or a curvature to it. So here we have two alpha helices, which they themselves are helical in nature. They're twisting around each other in a helical fashion. So this is a helix of helices, right? We call it a coiled coil arrangement. Okay, so that's how we have our fibrous arrangements. They're coiled coils, for example. And that's how keratin is made. Another example of that, and it's kind of more important to hold us together. Without this molecule, you would be a puddle of goo with bones sticking out of it, is collagen. So collagen at the bottom is what's called a triple helix. Okay? It's not an alpha helix at all. Right? An alpha helix is where it folds on itself. Here you have three strands which are mutually folding around each other. It's kind of like braiding your hair, but this is not a braid. A braid is where things cross over each other. It's like taking three hairs or three wires and twisting them around each other as you go. So sort of like a steel cable, where you take only, steel cables clearly have more than three components in them, if you ever looked at a cable. But imagine a cable with only three components to it, three little wires in it, three little steel wires. You twist them around each other as you go down. And this provides strength because they're pushed on each other. And its sequence is very, very simple. It's glycine, proline, proline, glycine, proline, proline, glycine, proline, proline, and repeats indefinitely, right, for however long it needs to be. Well, we know with all those prolines, the chance of it forming an alpha helix is zero, right? It's not going to form an alpha helix. What it's forming is called a triple helix. And because the glycine occurs every third amino acid, and there are three strands, all their glycines could permanently face each other. It's like they're in lockstep with each other as the three twist around. And being glycine, it's small, virtually non-existent R group, they can get really close together. And that's shown in panel B at the bottom. And all the prolines stick out around the outside. So being full of glycine in the center and nothing but prolines on the outside, this molecule is very hydrophobic, right? It doesn't interact with lots of things. So how do we anchor the cable to one end or the other? We got to think back a couple lectures. We put functional groups on it that could interact with other things, like hydroxy groups. So if we make a hydroxyproline near the end of this thing, it might interact with something else, right? That's what we need to do to make our collagen functional, right? So how do we put a hydroxy group on it? Well, we need an enzyme, right? We have an enzyme called Prolyl Hydroxylase, and we'll talk about enzymes in the next block for exam 2, but it basically takes a hydrogen or OH donor, right, a redox donor, and puts the OH on the proline. Well, the donor for that is vitamin C, or ascorbic acid. So what happens if you don't get enough ascorbic acid? So what happens if you don't get enough vitamin C?
So scurvy.
Scurvy, right. So when you don't get enough vitamin C, you don't have enough cofactors for this prolyl hydroxylase, and our repair and replacement of our collagen isn't going to be very complete, right? 100%. So things that attach muscles and tendons and bones to each other aren't being repaired well enough. So your infrastructure is being compromised. So bones tend to warp and not bond correctly, and tendons and ligaments become weak and so forth, and we call it scurvy, right? So the misconception about vitamin C, and it's a problem misconception because it's been promoted incorrectly by someone who won a Nobel Prize, is that it has nothing to do, but you can't take vitamin C to cure things, right? It's not a cure your immune system or boost your immune system. I know the retail on that is ridiculous. There's a profit from it, but that's not why you take vitamin C. You need vitamin C for two reasons. One, to do this hydroxyproline, and the other to act as an antioxidant in the water-soluble parts of your body. But let's say you're on a voyage across the Atlantic, say 500 years ago, and you need your vitamin C, and you're not going to come across any orange trees along the way. So what do you bring with you on this voyage? Because we don't want these sailors not getting their vitamin C. What do you bring with you? You're going to be out at sea for months. We need to bring some source of vitamin C, and the vitamin C tablets aren't around yet. You got to wait another 400 or 500 years for that. So maybe you think you'll bring a barrel of oranges with you. Well, those will be rotten within a month. Can't keep it. They're not going to grow in salt water. You're going to run out of oranges quickly. So what do you bring instead?
Orange juice.
You could try bringing orange juice, but remember we're in 1400s, not 1900s, and canning is very good. You're not going to get a good seal. You may get a few sealed well, but not for a crew, and you're going to run out of orange juice quickly. At least good orange juice. So we need something that won't rot or won't decay. What do we bring with us that'll last longer than oranges? How about we bring a barrel of limes with us? Limes can be stored for much longer than oranges. They don't rot nearly as fast. So we could do several month voyage using limes. But do you really want to go bite into a lime? Doesn't sound pleasant, right? So what the sailors did is, it's time, you got to go down below deck, grab your orange, or your lime. You need to eat this. They had a compromise. I'll only do this if I get to wash it down with rum, right, or some sort of alcohol to ease the pain of just biting a lime. So we still do this today, but not so much to get our vitamin C, but you put limes in alcoholic drinks, and it stemmed from that practice at sea. Okay. Right, moving on to our second type of protein, our globular protein. This is the one that kind of folds on itself, right? It's soluble, it stays in solution in water. The exterior surface of it will have hydrophilic amino acids or polar amino acids. That doesn't mean that can't have a hydrophobic one on the surface occasionally, but it'll be a majority hydrophilic or water interacting amino acids. Whereas the interior will be mostly hydrophobic amino acids, right? Or your non-polar amino acids. That doesn't say you can't have a tyrosine or a serine down there, or even an aspartic acid down there. But you probably won't have as many in the interior as you will on the surface. Okay? An example of that shown on the right in carbonic anhydrase. It's one of our enzymes we'll talk about later. But you see it's formed up in this round or globular or globe shape, a spherical shape. Right? The little white dot in the center is just a metal ion that it holds, the zinc that holds the thing together. And we could have some histidines or serines that interact with the metal to help maintain the shape. Okay? And our last type is called membrane proteins, and those are the ones that are embedded in membranes. And we have different degrees of embedding into the membrane. Right? So I have an analogy for this as well. So if you see this lipid bilayer there, and if you think about the proteins that are completely embedded in it, and that's the three that actually have contacts with the interior. So this one in the middle looks like a big bone, but it's not a bone, right? So there's some strands going across. They could be alpha helices, it could be beta strands, but it's embedded in the membrane in some parts, right? The one on the left also crosses the membrane. It's also a transmembrane protein. And the one on the right, only part of itself is embedded in there, but it doesn't cross the membrane. That doesn't preclude it from the category. It's still an integral membrane protein because part of itself is in the membrane. The latter two, or the former two, the middle one and the left one, are called transmembrane proteins, but they're still integral membrane proteins. They're in the membrane. Okay? So if you think of these integral membrane proteins, they're in the band, right? They're the band members. They play the drums and the guitar and the lead singer, right? They're in the band. The ones above it, you notice, don't really interact with the membrane that much. They may make a few contacts with the surface, but they're mostly interacting with the band members. So these peripheral membrane proteins are the band's groupies, right? They're not actually in the band. We still group them in the membrane protein category because they hang out with the band members, but they're not in the membrane, so they're not in the band, right? So the ones that are embedded in the membrane have to have at least part of themselves in the membrane. Those are integral membrane proteins. They're integral to the membrane. Whereas the peripheral ones literally only stay on the periphery, right? Those are the band's groupies. They just hang out with the band members. They're not in the band, right? And then if you're neither of those, and you're floating around in the cytoplasm, you're our globular proteins. You're not a membrane protein at all. All right, some of these membrane proteins can act as channels. They might have a path through them, like our beta barrel we talked about earlier. It's not the only way to do it, but this is one example. And you can have a channel that may or may not have a flap on the surface. That flap could open and close depending on certain stimuli, possibly a voltage change or a ligand binding or a salt molecule being in higher concentration on one side than the other. So lots of ways to make this thing, even light, that's how you're able to see the screen right now, is because a channel is open and closed by light binding to it, a photon being the ligand, right? So why this thing is buried in the membrane across it has to be able to reach the other side. I know the interior of the membrane, is hydrophobic, but the lining of this channel is probably a hydrophilic lining to let these charged molecules, be them small ions or glucose or whatever it might be, to go through. Whereas without this channel, there's no way these red molecules are going to get across this membrane. There is one exception to that, and we still don't know exactly why, but water, being very polar, can somehow easily cross this membrane. And even devoid of channels, right? It can still cross, but no one's quite figured out exactly how that works yet. So when one of you do it, I want to hear about your Nobel Prize. Okay? And lastly, for this, well, almost lastly, we can still do tertiary or quaternary, but between secondary and tertiary structure, we have something called super secondary structure. So it's in between the hierarchy. It's not an alpha helix, it's not a beta sheet, it's not a loop, it's not a turn. Those are all secondary things. But it's not the whole protein. We call that tertiary. It's somewhere in between. So somewhere in between secondary and tertiary is some combination of things. For example, here we have a helix turn helix on the far left here. So it's an alpha helix, makes a little turn, and then another alpha helix, kind of like a dance move, right? The helix are the individual steps of a dance, and the loop is another individual, or the turn is an individual step. But if you put them together, it's helix, turn, helix. It's a dance move, right? It's not an individual dance step, which would be a secondary thing. And it's not the whole dance, which would be the entire protein. It's somewhere in the middle. So we call it a motif, right? It's a fancy move you're making with a combination of a few steps, but it's not the whole dance. So this helix, turn, helix represents a motif that we see that occurs often. So we gave it a name. It's simply called helix, turn, helix. Right? And it occurs very often. In fact, there's another one in the same protein here. There's a helix up here, a little turn, and then another helix. Okay? We could also have a helix loop helix. The only difference being the loop is a little too long to be called a turn. So it just gets the name loop. Okay? The coiled coil we saw earlier, right? So it's two alpha helices coiling on each other. It's a little bigger than just a secondary element. It's several secondary elements, several dance steps put into a move. So we call it a coiled coil. Right? C is also one of those where we have a helix, a little turn, helix, a little turn, another helix, a loop, and then one that goes along the back. And maybe these two are cupped by that one, right? So they fold into each other. That's called a helix bundle. They could be parallel, anti-parallel, doesn't make any difference. Okay. So here's some little bigger structures. So these aren't just simple dance moves that you make with a few steps. These are more choreographed. It's not the whole dance routine. That might be several minutes long. But this is a small segment where you're doing something specific, right? Over and over and over. We get the idea. It's a certain dance move you keep repeating. So here, these are called domains. And what that is it's not the whole protein. So looking down here, any one of these colored elements, like the blue one, for example, the blue one is kind of a self-contained thing. Right? So this is the self-contained, it kind of folded on itself. It's got this arrangement, but it's not the whole protein. This is one long strand that keeps connecting to each other. So it didn't fold up as a single protein. It folded up as independent domains. So we call each one a domain. Right? They could be long, they could be fairly short, but it's not the whole protein. Okay? Right. The very last part of that is something we call folds. Now, a fold is not really in the hierarchy of structure where you had primary, secondary, and then this group of supersecondaries like motifs, and then domains, and then we had tertiary, and then we'll eventually get to quaternary. What a fold is kind of outside that structure, and I'll use another analogy to explain it. If I asked you to describe your car, right? You describe first it has an engine, it has tires, it has a steering wheel, it has brakes, it has a trunk. All those are elements that virtually every car has. So that's kind of like your primary structure. Yes, I agree it's a car, I agree it's a protein. What order you assembled those might be its primary structure. Then you go, well, it's got an automatic transmission versus a manual. Oh, you've got an alpha helix instead of a beta sheet. Okay, that's cool. So secondary elements could be distinct between cars. And then we zoom out and see the whole car. You go, oh, it's actually a truck versus an SUV versus a sports car. That's your tertiary structure. You're describing the whole car. But in fact, you bought one that's actually two cars that have been smushed together. Not a good purchase. So it has quaternary structure. They're fused together now. Not a very functional car at that point. But then I ask you another question. What color is your car? That's kind of independent of any of those previous questions, right? You could have any car be any color. That's what our fold is. So our fold is, yes, I agree, you have a car, it's got this type of tire on it, you got these aluminum wheels instead of iron wheels or whatever, it's got a spoiler or something. You're describing all sorts of elements, but then I ask you what color is it, and you say, oh, it's white, right? Or I've got a green car, or whatever it might be. That's the type of fold this protein is. So many proteins can have the same fold, but they don't look alike at all. They don't have the same sequence. They don't have the same secondary elements, at least not all of them. So you can have a white truck and you can have a white Ferrari. They're still the same fold in our sense here, in our analogy, right? Or it's a blue car, or a black car, or a green car, whatever it is, right? So in this case, if it's a beta barrel, it's a beta barrel. It might not have the same function at all. It might let chloride ions through this time instead of sodium. So it's not the same protein at all, but they share a fold. And there's only been about 100 or 150 so folds ever identified. There's only so many ways to put proteins together, right? And that's what a fold is. Okay, so it's kind of outside the hierarchy, right? And our last one will be quaternary structure. So if we take our protein here at the bottom, like myoglobin, it has a tertiary structure that's folded up into this one thing. And I take several of those and put them together. I get something that has multiple proteins attached to each other. And that's going to be quaternary structure. So in quaternary here at the top right is a hemoglobin molecule. It's got two yellow or yellowish orange subunits and two green subunits. Each individual subunit looks like a myoglobin molecule, but together all four make a hemoglobin. They're not identical to myoglobin, but they're close, right? And each one has a heme group with an iron in the center of it. This is how you carry molecular oxygen around your body in the blood. Okay? But how do we describe quaternary structure? Well, we can say this one has 4 subunits, right? And so we call it a tetramer, mer meaning parts, right? So a monomer is 1 part, a dimer is 2 parts, and so forth. So a tetramer has 4 parts. So if I told you I had a dimer, there's 2 possibilities for a dimer, right? So a dimer meaning 2 parts. The 2 parts could be identical to each other. We're going to call that a homodimer, the prefix homo meaning same. And we could also call it, if they're not the same as each other, we could call it a heterodimer, hetero meaning not the same. So a homodimer would be 2 identical proteins binding to each other to make the overall structure. A heterodimer would be 2 proteins that are not identical binding to each other to make the overall structure. Both have the same number of subunits, 2, but one's a homodimer and one's a heterodimer. That should be very simple to understand the difference. Let's move on to 3 subunits, and it gets a little more complicated here. If I said I had a homotrimer, you know what that looks like. That's all the information you need. It's 3 identical proteins coming together to make this complete unit. Okay? If I said I had a heterotrimer, there's still some ambiguity in that. Do you mean I have 3 completely independent subunits, none of them look like each other? That's a possibility. Or I have 2 of one type and 1 of another. That's still a heterotrimer because they're not all the same. Hetero doesn't mean they all have to be different. Hetero means not same. So if I say I had a heterotrimer, it means do you mean 2 of one and 1 of another, or do you mean 3 different ones? Well, that's ambiguous. I need more information. So when we have an ambiguity like that, unlike we had for heterodimer, there's no ambiguity. There's 2 different ones. So here I have to label it somehow. We do it like chemical formulas. I'll call it if it has 1 of one type and 2 of another type, or so let's say 2 of the first type and 1 of another type, alpha 2 beta. And I assume the beta has a 1. Like you do in chemical formulas, like water, you write H2O. You don't write H2O1. The 1 is understood. Right? So in terms of water, if each part, if the atoms were really proteins and you had 2 of one type and 1 of another, it would be a alpha 2 beta heterotrimer. Right? But what if it's not that? Let's do a more analogous like hydrogen cyanide. It's HCN. All the atoms are different. Right? If you had a protein assembled like that, 3 different subunits, which are nothing alike, right? You would call it an alpha, beta, gamma heterotrimer. Does that nomenclature make sense? You just give each type of subunit a Greek letter, like you would a chemical formula. You give it the element, and then you list how many it has. And if it's only 1, it's understood. You don't have to write it. Okay? So for hemoglobin at the top right here, what would you call this thing? It has 4 subunits. 2 of one type and 2 of another.
Heterotetramer.
Okay, that's one part of the name, but by heterotetramer, I'm still unsure. Do you mean all 4 are different? Is there 2 of one, 2 of another? Is there 3 of one and 1 of another? Is there 2 of one and then 1 of each of the others? There's lots of possibilities here. Which one do you mean? So
It would be the alpha 2, beta 2.
okay, so say them together.
So an alpha alpha beta dimer.
So you keep leaving out parts. So it's alpha 2, beta 2, heterotetramer. It's not a dimer, it's a tetramer. So when you give the name, you give me the unambiguous list if necessary. It's not necessary for heterodimer, right? But this one is necessary. I need to say alpha 2, beta 2, heterotetramer, because it has 4 total parts. That's how you name these. And that's how you describe quaternary structure. If I'm talking about myoglobin, and myoglobin only has 1 chain, it truly doesn't have quaternary structure, and we just call it a monomer. There's no, the hetero and homo prefix are meaningless because there aren't more than 1 subunit. So it's just a monomer is what we call the ones that don't have quaternary structure. Okay, so here's some examples. If you have the top left here, we have 2 subunits that are identical to each other, one drawn in pink here, one drawn in yellow, and they're bonding to each other to make the functional unit. A lot of proteins work this way. A lot of proteins that cut nucleic acids work this way, like your endonucleases, right? If you're in lab, we're talking about those pretty soon, right? So this would be called a homodimer. No prefix of subunits necessary because I know it's 2 of the same thing. You could call it alpha 2 if you wanted to, but it's redundant. Okay. In panel A here, we have hemoglobin again, 2 of one type, 2 of another, alpha 2, beta 2. Okay, so let's talk about some examples. At the top here, identify your level of protein structure based on the description. So in choice A, we have a beta pleated sheet. Which level of structure is that?
Tertiary.
So a beta pleated sheet is
Or secondary.
Secondary, exactly, because it's just one secondary element held together by all that hydrogen bonding between the backbone features. The choice B, order of amino acids in a protein.
Primary.
That's the primary structure. That's a piece of information of the primary structure, exactly. C says a protein with 2 or more peptide chains. A chain means a complete sequence N to C. We have 2 or more of those put together.
Quaternary.
That's quaternary structure, exactly. The shape of a globular protein. That information is contained in
Tertiary.
tertiary. Right, that's an example of the tertiary options. Again, held together by lots of things, right? And then a coiled coil of alpha helices.
Quaternary.
Super secondary.
Super secondary, right? So a coiled coil of alpha helices may not be describing the entire protein. I'm looking at a small segment of it or how it's put together. So a coiled coil could be describing just a small segment of it. And it's more than one just secondary element. And of course, it's the only choice left here, but it's bigger than one secondary element, but not yet the whole protein, so we're going to call it supersecondary. Another possible right answer for coiled coil would be a motif, right? If that's one of the choices. The motifs we can do. If I gave a choice, like let's say choice F here, read, it has the resemblance of beads on a string. What level of structure would that be?
Primary?
No, I'm describing not the sequence of amino acids, but after they've all folded up, it looks like beads on a string. So it's a repeating unit. It looks like the beads folded up independently, and they're attached by little tethers on a string. This is, again, supersecondary.
Tertiary.
This is supersecondary. I'm not seeing the whole protein. I'm just seeing the repeating unit in the protein. So I'm seeing a domain, right? It folded up independently, and we had a picture of that on one of the slides, and it just repeats over and over. Right? But if you do see the whole protein, right, that's like choice D, the shape of the whole globular protein, that would be tertiary. Okay? And the last thing I want to talk about is protein hydrolysis versus denaturation. And we'll do this as an experiment when we get to the lab, for those of you in the lab. But the two words mean different things. Denaturation means to lose its nature, or to lose its natural order, right? We did this for DNA. For a DNA molecule to denature is for the two strands to come apart. Well, that's not very detrimental to DNA. It can come back together, right? RNA the same way. But if you have a protein and you denature it, the complexity of the fold, it's much more complex fold than, say, a simple double helix. It's very unlikely to renature spontaneously, right? So when you cook an egg, it's exceedingly difficult to uncook it, right, by lowering the temperature. Now, it is possible to do that for much smaller, less complexly organized proteins. But in general, once you denature it, it's denatured. Okay? But if I denature a protein, which levels of structure are still intact?
Primary.
Only primary, right? I have not broken any peptide bonds, right? I've unfolded the protein, and basically it's a long string of spaghetti now, right? So primary structure is not disrupted by denaturation, but all other higher levels are. Okay? And hydrolysis, what that refers to is lysis, or breaking of a bond. And we're talking about the peptide bond here. So if I break the peptide bond, right, what level of structure am I breaking?
Primary.
Primary. And if I break primary, nothing higher order will survive. So for denaturation, I'm breaking everything except primary, because it's still together. Right? But in hydrolysis, I'm literally breaking the bonds that hold primary together, and all higher levels of structure will no longer exist. It'll fall apart. So without primary structure, the protein won't exist. It'll fall apart. So denaturation breaks everything except primary. Hydrolysis specifically breaks primary, and thus everything higher. Right. And the next couple slides explain, I won't go into it in too much detail, but how they fold together. There's actually two basic models. I know it lists three on the screen, but the last one, the third one, is actually a combination of the first two. It's how we've decided proteins generally fold. It's an entropic method and a molten globular or nucleation searching method. But I don't want to talk about these too much in here. We'll talk about them more in lab. Okay? And some neurological diseases that result from misfolding. Really quick, at the bottom here, you see a protein labeled A and B. Right? So if the protein is normally folded as A, you see all that bundle of alpha helices. I'd call that a 4-helix bundle, as you see right in panel A there. But if this protein is heated, or gets the wrong conditions, or the salt's just not right, or it encounters some conditions that make it fold a little differently, those two alpha helices nearest to us may rearrange into another stable arrangement with a 4-stranded beta sheet. Right, so we have a beta sheet there with 4 strands. It's kind of a mixed sheet, but it's another stable arrangement. However, when I rearrange those alpha helices, The normal amino acids that we're phasing out, that were hydrophilic and interacting with a solvent, aren't necessarily phasing out anymore. So we have a hydrophobic surface that's exposed. And this protein would love to bury that surface, right? Make it not exposed to solvent. So it talks to its neighboring identical protein and says, look, if you form, it doesn't really speak to it, I'm just anthropomorphizing a protein here. It tells its neighboring protein, if you rearrange yourself into the beta sheet, we could stick together, right, and bury our surface. And because there's that impetus to bury the surface, the second ladder protein adopts the same shape. So it goes from being the alpha helix to the beta strands as well. And of course, this chain reaction propagates down these proteins, and they all start becoming these beta sheet form, and they start sticking together, right? So this normal protein has now adopted a different shape, and they all start sticking together. And when it starts sticking together in these big aggregates, they're no longer soluble in water, and they fall out of solution. And that's detrimental to the cell. It's debris in the cell we can't get rid of, and it's propagated by the protein itself. These are called prion diseases, right? For the protein is the unit of the infectious unit, right? It's the protein that's the infectious agent. It's not living, but a misfolded protein is responsible for other misfolded proteins, right? This is how we get things like Alzheimer's, Parkinson's disease, mad cow disease, and stuff like that. So how do you get something like that? Well, the main way, and I'm not saying this is the case for Alzheimer's and Parkinson's and so, but for mad cow disease it is. And in humans it's called Creutzfeldt-Jakob disease. But if you have a protein that gets partially digested, right, sort of hydrolyzed and not completely fallen apart, sort of denatured, and you feed it to the same species, we're talking cannibalism here, you feed it to the same species, they're going to ingest it, and they go, hey, we need a protein like that. Let's completely degrade this thing and send it to where it needs to go. So it might end up on the outside of a cell or something, and if it's in that extracellular matrix, other proteins nearby are going to adopt the misfolded form, and they're going to start killing cells nearby. And you're going to get these plaques like you see in the brain image on the top. Right? So how does this happen? Well, if you feed cattle beef, this is going to happen. Right? So don't feed an organism to those organisms. Right? No cannibalism. This is bad. Right? So the same thing can happen if not necessarily for humans being cannibals, but if our protein is identical to the one in beef or in cows and bovine protein, we could have this problem. Right? So be careful. I'm not saying don't eat cows. I'm just saying be careful which proteins that if you're going to cook something, make sure you denature it completely, because this is a possibility for some proteins. And there are human diseases as a result of this.